And just to, oh, sorry, yeah. Just to add that we have a lot of people on the team. We had someone else, Rintaro Suda, who also joined with the editing the videos and the food model that, yeah, so thank you to him. And
our school is in Chiba Prefecture. Next to Tokyo is the capital of Japan. This is our school introduction video, but we don't have time enough to watch. So please watch from World Weather Watcher website if you want to watch. This is our school grounds. We have 4 fields and we then use them during the PE class or club activities. We also accommodate night games.
We'll explain a little about the type of extreme weather Japan experiences, typhoons, or kind of like cyclones that we have. And in short, these powerful storms are characterized by high speed winds, heavy rainfall, and devastating storm surges. Can you please? First, the 2 simple ones. These storms frequently exceed sustained wind speeds of 170 kilometers per hour or 100 meters per hour, and gusts over 250 kilometers per hour or 155 meters per hour.
These are some of the devastating impact that these storms can cause. Immediate damages, like the Gulf Coast above, also are devastating, but long-term effects, like power cuts and like the destruction of sewage infrastructure, can also cause long-term damage. And a little bit next, storm surges are often overlooked, even though they cause like equally devastating damage. The friction between the eye wall and the ocean of the storm, in addition to the low pressure zone from the eye, lifts up the ocean, sending massive blocks of ocean over 20 feet high. And next, downbursts are columns of cold air that rapidly descend and hit the ground and produce a wave of wind exceeding 240 kilometers per hour. And damage is comparable to tornadoes, and the damage is below.
So some of us will be like, we did research on these sort of weather events, so that's why we added that. So thank you, those are acknowledgement.
Okay. So hello everyone again. Thank you so much for coming here. We would like to start our research presentation. My name is Yuta Suzuki and I am one of your moderators for this session. Next slide, please. The outline of our presentation is as follows. Firstly, we would quickly explain what Japan's weather is like. Second, we have 2 research presentations on accuracy evaluation. Thirdly, also 2 presentations on location difference. And fourthly, 4 research on specific weather conditions. And lastly, 2 presentations on agricultural applications. Some research might be hard to understand, but please don't worry. We're going to take a question time after each section, except for the first part. So if there is something that you do not understand, or if you have something you would like to ask, please feel free to ask us during the question time. Given that, we would like to start the first part of our presentation, Japan's weather. Japan has 4 different seasons. Spring, which is from March to May, has mild temperatures and cherry blossoms in full bloom. Summer, which is from June to August, is very hot and humid, but also has a rainy season. Autumn, which is from September to November, has cooler weather with beautiful red and yellow autumn leaves. And lastly, in winter, which is from December to February, is cold with heavy snowfall in northern and mountainous regions. The rainy season lasts from June to mid-July, bringing steady rain in Japan. And the typhoon season runs from May to October, with the most storms in late summer and early fall. And this is our brief explanation about Japan's weather. We will dig further in detail throughout our presentation. So Now we would like to move on to the second part, the basic research about accuracy evaluation. And today I am pleased to present my research on the accuracy evaluation of the GSMap and discuss possible factors influencing its performance. The purpose of the study is twofold. One, to evaluate the accuracy of GSMap, a satellite-based precipitation estimation system. Two, to identify factors that influence its accuracy and explore ways to improve its reliability for future applications. To investigate the accuracy of GSMap, I compared its precipitation estimates with actual precipitation data by the Japan Meteorological Agency, JMA. So some observation details. The data for the study was collected from the Yokohama Meteorological Observatory, and the observation period covers January 1st, 2020 to December 31st, 2024. And this is where Japan is located in the world map. And next slide, please. And Yokohama is just around Tokyo. To quantify the relationship between GSMap estimates and actual precipitation, I calculated the correlation coefficient, which measures the trends of association between two variables. It ranges from -1 to 1, and when it's close to -1 and 1, the correlation is strong. However, when it's around 0, the correlation is weak. The overall correlation coefficient was 0.82, indicating a strong positive correlation between GSMap estimates and JMA observations. However, as you can see in this graph, some differences still exist, which led me to investigate possible causes of inaccuracy. And so the big blue line is the average, and the others show that correlation for each year. Examining different time frames, I noticed some significant weather anomalies that might be I didn't examine the correlation between precipitation levels and accuracy. Surprisingly, the correlation coefficient was 0.14. This result suggests that precipitation amount itself does not significantly affect accuracy. If precipitation is not the main factor, then what is causing the variations in accuracy? Examining different time frames, I noticed some significant weather anomalies that might be affecting accuracy. August 2020, the average temperature increased by 1.76 degrees Celsius compared to normal levels. September 2021, Japan was struck by 3 typhoons. And in July 2024, the monthly mean temperature deviation reached plus 2.16 degrees Celsius, indicating an unusual rise in temperature. Based on these observations, I propose the following conclusion. Temperature and extreme weather conditions play a key role in determining GSMap's accuracy. If this conclusion is correct, further research could help refine GSMap algorithm to adjust for temperature and weather variations, improving its performance. In summary, firstly, GSMap shows a strong correlation, 0.82, with actual precipitation data, but inaccuracies remain. Second, precipitation amount itself does not significantly impact accuracy, as shown by the low correlation, 0.14. But lastly, temperature and extreme weather conditions may be key factors affecting GSMap's performance based on observed weather conditions. I hope this study contributes to further enhancement of the GSMap. Thank you for your time and attention.
My presentation is about the differences between rainfall data observed from satellites and rainfall data observed from the ground. I collected rainfall data in Yokohama, Kanagawa, Japan. This graph shows the difference between daily GPM data and JMA data, with the vertical axis shows JMA data minus GPM data. As you can see, the differences are surprisingly large. Therefore, I decided to investigate when these differences become significant. I compared GPM and JMA data on a daily basis from 2020 to 2023. This graph extends the previous one over a longer period. The points where the differences are large are marked with red circles. To analyze this in more detail, I created a table ranking the days in order of largest differences. The reason for this difference is often caused by typhoons, fronts, and low-pressure systems. However, since the difference can sometimes be larger in GPM data, and other times in JMA data. I expanded the range of the table. The blue color indicates that GPM data is larger, while the red color indicates that JMA data is larger. Looking at the overall trend, blue is more frequent, which shows that GPM data tends to produce larger values than JMA data. Furthermore, since JMA data is generally accurate, it was found that the GPM data tends to show larger values than actual rainfall data. In fact, even in the total rainfall over the 4 years, GPM data shows larger values compared to JMA data. From this, it becomes clear that the differences tend to be larger from summer to autumn. Finally, as mentioned earlier, while some low-pressure systems create significant differences, others do not. I would like to investigate the differences between these types of systems, and I want to investigate why GPM data tends to overestimate rainfall. Thank you for listening.
My name is Takuma Umeshita, and my title is How to Get Accurate Rainfall, and my objective through this research at Tarama Island is to improve the accuracy of measuring rainfall. Where is Tarama Island? It's located in Okinawa Prefecture in the west of Japan, at the red point in this map. And previous presenters researched at Yokohama, the blue one, because our school is located in Yokohama. But I focused on Tarama Island because of its unique terrain. It's made of elevated coral reefs, so the entire island is flat with almost no rivers or mountains, and I think there is no need to consider errors in rainfall caused by such things. I compared GMA and GSMap data from 2020 to 2024 by using monthly data. The reason I utilize GMA data is it measures actual rainfall. These figures shows monthly views of GMA and GSMap data. Oh no, the blue line has disappeared from July to September in 2023. Don't worry, this is because they are almost identical. And looking at the correlation between GMA and the GSMap data, I found there is a strong correlation for every year from 2020 to 2024. However, comparing the GMA and the GSMap rainfall for each month, it's clear that the amount of rainfall considerably, especially on March 2024. Sorry. So I think GSMap may not be measuring rainfall accurately. Why might it not be measured accurately? I think that the cause might be the rain clouds, since GSMap looks at the rain clouds. In order to compare the rain clouds from the ground and the satellite and see the data in more details, I look at the data on daily basis to make it easier. These pictures show rain clouds seen from GPM. There were no rain clouds above Tarama Island all day, but looking at the rain clouds from the ground, you can see that Tarama Island was covered with them. Another example shows rain clouds being captured, but GPM couldn't detect these strong rain clouds well. That's why I discovered that the rain clouds captured from the ground were out of sync with those captured by the satellite. In the future, I'd like to investigate how to eliminate this discrepancy, and in doing so, improve our forecast and countermeasures. My final goal is reducing damage by disasters. Thank you for listening.
Hello, I'm Harumi Sakaue. Today, I would like to give you this presentation about comparison of monthly rainfall data. I wanted to know the difference between GSMap's monthly rainfall data and the local data of the JMA. The purpose of this study is to find the relationship between topography and the difference of GSMap and JMA. I surveyed these 4 sites, Yokohama and Osaka in plain coastal areas, and Chichijima and Hahajima are small islands which are 1,000 kilometers south from Tokyo. I looked at data from 2020 to 2023. First, I took the GSMap and JMA monthly total rainfall data and the quotient of GSMap and JMA value for each month at Yokohama and Osaka. And I made graphs of the quotient and the JMA data. We can see that the quotient of the GSMap and JMA data becomes smaller as rainfall data increases. And in most cases, GSMap values are larger than the JMA ones. Next, I studied Chichijima and Hahajima in order to compare Yokohama and Osaka. They are small islands, so the weather there is less affected by their topography. On Chichijima, when rainfall data is large, the difference is small. However, on Hahajima, the reverse is true. On both islands, the GSMap values are smaller in most cases. Therefore, I investigated the characteristic rainfall data in these 5 months. As shown in the table, these top 4 months have the largest rainfall data by fronts. And comparing the difference between GSMap and JMA values, I think there's a relationship that their rainfalls may be causing the difference. And in this month, had rainfall by a typhoon, but the rainfall data and the difference value is far apart, here and here. So it is unlikely that this rainfall caused the difference. In other words, we can think that GSMap can observe typhoons, but not fronts. To check the accuracy of this thought, I examined 2 months of data for each at Yokohama and Chichijima. It is difficult to determine if rainfall is observable due to the cause of rainfall because the rainfall data and the difference values are so far apart, this and this, in any month. In other words, the Hahajima data suggests that GSMap captures typhoons but not fronts. But looking at other places, this is not necessarily. However, I think it is possible that there are rainfalls that don't exist but GSMap captured, and the rainfalls that exist but GSMap didn't capture. Also, the GSMap values are often larger for the plain coastal areas, but for the islands, the reverse is true. And except for Hahajima, the difference becomes smaller when the actual rainfall data is larger. From now on, I have many questions to solve, like top of that. The final question is finding reasons for the trends in the plain coastal areas and on the islands. Thank you for attention.
Hello again. I'm here to present the project Comparing Typhoon Data and Exploring the Reasons Behind the Differences Between JMA Data and GSMap Data. Okay, To start off, let me first introduce Typhoon Faxai. And these are all the basic information about the typhoon. Most notably that it's category 4 and about 930,000 houses were without power after the typhoon. So it was really big. Our project is, in short, a comparison of typhoon data and exploration of the reasons behind the differences or errors of GSMap compared with JMA. And there were no instruments able to record typhoon data in the area where the typhoon landed. So, and also judging from the fact that category 4 typhoons are predicted to increase as global warming proceeds, it's crucial that we improve GSMap's accuracy to better predict and prepare for disasters in the future. Our purpose is to help reduce errors in the GSMap forecasting system in the long term. We started with this typhoon because it coincidentally passed over our school grounds, and our weather data logger had recorded some precious data on that day. So these are the 3 places that we'll pull data from, and our school is right where it landed. So, yeah. The first graph is the comparison of precipitation of GSMap and JMA at Chiba City. And the differences increased at 5 a.m., exactly when the typhoon landed, no, not landed, when the eye passed by, as derived from the below atmospheric pressure graph. So this is another graph of the same typhoon at a different time that passed over Miura Peninsula, and parts of which is a part of Chiba. The same can be said as the first example. This is yet another example from the Sakahata region of Chiba, with the same results, though not as apparent as the last 2. So from the data we collected, we noticed that the differences increased drastically when the eye of the typhoon passed over. So why is this? We came up with 2 hypotheses. And our first hypothesis is that GSMap records are created by taking the average of an 11 kilometer times 11 kilometer square. And so the fact of the eye and the eye wall is reflected excessively. For instance, the below example. So the wind speed, not the wind, the rainfall is at 90 millimeters per hour at that location. But since it takes the average of the surrounding region, it's showed as 60 millimeters per hour. This is an actual example from that typhoon that reflects this, 10 millimeter and 90 millimeter, which is like a huge gap. So that was one hypothesis. This is our second hypothesis, that GSMap may not be able to accurately discern areas with lots of rainfall, or that radar data is reflected at a slightly shifted location on the finished map. So we decided to go further with the second hypothesis, and here's more of our thoughts. The GSMap shifts in data are usually to the side of a larger body of water, for instance, the ocean. And we thought that due to the radar's qualities, it could be misinterpreting water vapor or moisture supplying the typhoon with the actual precipitation. To validate our series, we decided to simply keep on processing large amounts of data from the past 20 years that was shown to make landfall according to GSMap data. And it's important to use data that's landed according to GSMap data, because we can't compare data that's from the ocean, because JMA only reflects data on land. So we will compare in the future these 2 points. 1, the location of the eye in the area with the most rainfall. 2, the location of land in the area with the most rainfall for both before and after the typhoon reached land. Yeah, I'll just spend more time on that side because it's probably difficult to understand. Yeah. So to conclude all of our points, we did in-depth analysis of Typhoon 50 that landed in 2019, Typhoon Faxai, and compared what was a comparison of GSMap and the MADIS or JMA data. So that's our next steps: analyze past typhoon data, divide into patterns, to consider ways to correct those errors in typhoon data. Thank you for listening.
Good morning, everybody. I'm Yuki Kanayama.
I'm Yumi Kotaka.
We would like to present the results of our research on precipitation errors in typhoons. We used JMA and GSMap. Last year, a big typhoon approached Japan. We wondered how accurate typhoon observations were from the sky. We selected 3 cities in Kyushu after the typhoon hit. That is Kyushu. In fact, Maryland and Kyushu are roughly equal in area. The results showed inaccuracy more than expected, so we decided to conduct additional studies for other typhoons of Kyushu. We chose 3 observation points: Kagoshima, Kumamoto, and Oita. These 3 cities are located in this part of Japan. The typhoons studied were Typhoon Sansan and Typhoon Namado. The survey method was to compare hourly rainfall amounts to obtain correlation coefficient, and after obtaining the average precipitation over 6-hour periods, the correlation coefficient were obtained by hourly shifting the range. Look at this data. You can see that the correlation coefficient of the 6-hour moving averages are greater than the correlation coefficient of the hourly averages. In other words, GSMap can't observe accurate hourly precipitation, but can observe typhoon.
The difference between JMA and GSMap observation for Typhoon Sansan was then plotted on an hourly basis. The results show that in all regions except Oita, more precipitation was observed in GSMap before and after the passage of the eye. And conversely, less rainfall was observed 6 to 7 hours after the passage of the eye. And other hand, 2 large discrepancies, this and this, were observed at Oita, where less precipitation was observed than the actual amount as the typhoon approached, regardless of the position of the typhoon. Similar results were obtained for Typhoon Namado. Furthermore, we selected cases where the difference between observed values between the JMA and GSMap was 5 millimeters or more, and categorized them into 4 directions: northeast, southeast, southwest, and northwest. The results show that the largest difference occurred at observation point in the northeast directions. This blue one. This suggests that the force on the right side of the typhoon directions of movement becomes stronger due to the influence of the Coriolis force, which may be influencing the differences in observation data. The above results show that GSMap data can be inaccurate when viewed at individual locations, but accuracy improves when analyzed over a wide area. Additionally, it has been found that there are time periods and areas where deviations are likely to occur during the course of typhoon. So it is thought that taking this into consideration will further improve the accuracy of GSMap data. Thank you for listening.
Okay, next, I'm Kyle, and I will be presenting about Koki Shinagawa, which is another student at our school, research about linear rain bands. Just a show of hands, like, does anyone know about or heard about linear rain bands before? Not many of you. So first off, like, what is a linear rain band? Although I'm simplifying, it's a type of cloud formation that precipitates concentrated rain, hence the word linear, for give or take a few hours. A clear example of this is this graph. And as you can see in the red line, over 100 millimeters per hour rain. To put this into perspective, here in DC, it rains about 70 millimeters during March. So this, in a couple of hours, it rained more than the entire month. And next, naturally, you'll be wondering, how? So they form by many clouds that form on top of each other, like this. However, research is still being done in the field, and it's still very much clouded in mystery, pun intended. Oh, sorry. Two more. Okay, next to clarify, moving on, I'll talk about the damage that is caused by linear rain bands. Because it's an extreme amount of rain, linear rain bands frequently cause landslides and floods, like the picture above. In Japan, this coupled with an earthquake can devastate whole communities for years and even decades. And next, as a final side note, the reason we started research was because a few months prior to this, several severe linear rain bands caused devastating damage. And we thought that we can use this research to improve the overall accuracy of linear rain bands in GPM. And next, to clarify, the difference between ground data and GSMap is that the weather radar only works around land, as the yellow area in the case over there. And on the other hand, GSMap uses over a dozen different LEO satellites, so low Earth orbit satellites, to measure precipitation around the. This is important because although ground data might be more accurate, we need GSMap data for data above the ocean, which is basically the majority of our planet. And as you can see, like an example of that is by utilizing GSMap, we can identify patterns that would otherwise be out of view. In this case, we can see that this linear rain band spans across Southeast Asia instead of just Japan. And then I'll explain what we did for our main research. First, to grasp a general idea of the difference of GSMap and ground observations, we constructed a graph. As you can see, it's obvious. The ground data, the orange line, and GSMap, the blue line, are completely different. To eliminate other possibilities, we analyzed if the difference in sensor equipment resulted in these errors. Since GSMap uses multiple satellites, i.e. the GPM constellation satellites, we thought these sensors resulted in these errors. And this graph, the bars represent what sensor was used. But however, we didn't find any significant correlation in this case. And this is our hypothesis for now. Since the satellites can't detect water vapor, they can't identify the vapor supplying the cloud with water. This leads to the GSMap algorithm misinterpreting the precipitation, in most cases underestimating the resulting rainfall of linear rain bands. Ultimately, in the future, we plan to expand on this theory by identifying more patterns. There has been limited, but some research papers highlighting the interaction between GSMap and orographic rainfall. We plan to look forward into this. Thank you. And
Hi, I'm Natsumi Yamamoto. I'd like to present about my research on internal structure of clouds using 3D rainfall watch, a tool provided by JAXA and NASA. Normally, a cloud's internal structure consists of two layers, here and here. In this figure, this blue area represents rain droplets, and a white area represents ice crystals. And that's green line marks ground plane, and the red line marks the boundary between ice crystals and rain droplets. I focused on boundary. I focused on boundary, which is generally parallel to the ground. This is because the water state varies as rain droplets and ice crystals depends on the temperature, which is changed with altitude. Look at this figure. This is a bomb cyclone which occurred in winter 2018, and also one of the big northeasters. Northeaster occurs 3 times a year annually along the U.S. East Coast. And in this case, the boundary is not parallel to the ground. And interestingly, the boundary intersects with the ground along the coastline. A bomb cyclone is a rapidly developing extratropical cyclone that occurs primarily in mid-latitude regions like the U.S. And here's land, like North American continent, and there is New York, and here the Atlantic Ocean. Warm currents in the Atlantic Ocean provide a large supply of water vapor. Northeasters often strike the U.S. from October to April, and some have caused devastating impacts. What does northeaster look like in terms of internal structure? As shown here, all 3 examples of northeaster exhibits a boundary that is not parallel to the ground. And sorry, I made a mistake, and this line is misaligned, so it's originally there. Sorry. Next. This leads me to study why these storms, particularly the January 2018 northeaster, display such interesting structures despite the common 2-layer composition of clouds. Analyzing these internal structure and relationship to rainfall could help predict future northeaster impacts. Factors that may influence the internal structure include temperature, humidity, and water vapor. I hypothesize the temperature difference between the land and the ocean was probably more affects the northeaster structure. In the winter, this difference was probably more pronounced as the land cools more rapidly than the ocean. To test this hypothesis, I compared the ocean temperatures with the land temperatures using Earth map provided by No School. The results show the temperature difference at least 50 degrees Fahrenheit between the land and the ocean during the January 2018 northeaster. Here's land. Here's land, and these rain clouds, wrinkles almost disappeared, almost like coastline. I aim to explore whether the position of ice crystals and water droplets within the clouds affects on rainfall. And notably, the intersection of the boundary between rain droplets and ice crystals with the ground closely matches with the coastline. And next. Specifically, this peninsula coastline, the warmer Atlantic Ocean waters probably influenced the cloud structure and on January 2018 northeaster. But what about the wave within the peninsula? To clarify the area and thermal energy needed to affect cloud structure remains a future work. Thank you for your attention.
Okay, good morning. The presentation so far has explained the accuracy of JPM. Now, we'd like to show the practical use of this data, assuming that it is reliable. specifically the relationship between precipitation and crop yield. My name is Shibuya Makuhari. Today, I'll present on the analysis of the relationship between apple yield and extreme weather in Aomori Prefecture using GSMap data. First, I'll talk about what sparked my interest on this research. Last summer, I saw a news report about extreme weather in Brazil. Because of extreme weather, orange orchards were destroyed and export has become difficult. And products using orange became scarce in Japan. After seeing this news, I thought if we could predict the impact of extreme weather on agriculture in advance using data, we might reduce the damage. So today, I'll introduce the result of analysis between GSMap data and extreme weather and apple yield using GSMap data. First, as a study area, I chose 5 key municipalities in Aomori Prefecture. Aomori Prefecture is the largest apple producer in Japan, which accounts 62% of apple yield in Japan. And these cities account for 93.5% of the apple cultivation area in the Aomori Prefecture, which is really important. As a method of my study, I analyzed precipitation, temperature, and sunshine hours from 2013 to 2023, and standardized yield per 10 yards for fair comparison. As a way of analysis, I use simple regression to examine relationship between the precipitation and yield, and multiple regression to assess the combined impact of climate factors. The analysis divided the apple groves into 2 phases: the flowering period, April to May, and the fruit enlargement period, June to September. For each period, climate data were collected to examine the impact of apple yield. Also, precipitation trends were analyzed by categorizing years into 2 groups: wet year, which precipitation exceeded 20% of the average, and dry year, which is fell below 20% of the average. And the black line, the dot line, is the average. First, when comparing GSMap precipitation data with ground-based JMA data, I found very high correlation coefficient of 0.897, indicating that GSMap provides highly reliable precipitation data. However, when I performed a simple regression analysis between GSMap and crop yield, I found almost no correlation, suggesting that precipitation alone cannot explain yield fluctuation in a statistically significant way. Next, I conducted a multiple regression analysis incorporating not only precipitation, but also temperature and sunshine hours. The results showed that approximately 27% of the total yield variation could be explained by these weather conditions. Among them, temperature had the greatest impact. Excessive heat can hinder pollination or inhibit proper fruit development and reduce yield. On the other hand, the impact of precipitation was relatively small. In our prefectures, farmers actively managed drainage and irrigation, which likely minimized the effect of rainfall fluctuations. This indicates that while GSMap data is useful for monitoring weather conditions over a broad area, predicting apple yield requires a more comprehensive approach that considers factors beyond precipitation, such as temperature and sunshine hours. Additionally, improving the analysis by considering not only total rainfall, but also qualitative aspects like rainfall patterns and short-term heavy rain events could further enhance accuracy. In conclusion, this study has confirmed the high consistency between GSMap and JMA data. For yield prediction, a
factor analysis that includes temperature and sunlight conditions is essential. Moreover, it is important to deepen the impact assessment of extreme weather, not only in terms of precipitation. For further analysis considering rainfall intensity and duration will be necessary, along with detailed monitoring using higher resolution satellite data. Thank you for your attention.
Hello everyone, we're Victor
And Joe.
Everyone might be tired, but this is the last presentation, so let's start. Today we'll be presenting research similar to the previous one, but with a broader scope. We analyze data from entire countries and regions, rather than individual areas. Before diving into the main content, let us explain why and how we conducted this research. First, about the why, the purpose of our research. The background. Precipitation is a key factor in agriculture. Optimal rainfall boosts crop growth, but excessive rainfall reduces yields. As an object, we aim to analyze the relationship between rainfall and crop yields, this time rice. Identify the optimal rainfall conditions for maximum productivity. Assess the risk of extreme weather events, droughts, and heavy rains on food productions. Next, about the how, our research approaches. First, about the area selection. We focused on 6 countries in East Asia this time. Next, the data analysis. We examined the correlation between annual precipitation and crop yields and the impacts of extreme rainfall, too much rain or too little rain, on food production. To measure climate, we use the drought index, which ranges from 0, which is fully saturated soil, to 800, which is complete dry. In other words, the higher the drier.
Okay, moving on to the main content of our research. We started off by comparing 2 countries, North and South Korea, which are both extremely close to Japan. Now, why do we choose these 2 countries? Because they're 2 geographically close and have similar climates, but economically different, meaning that they handle irrigation differently. While North Korea has limited irrigation, South Korea has a stable irrigation and are resilient against abnormal weather. So we first analyzed the rice production during the 2015 Great Drought, a rare event occurring only once in 100 years. As you can see, North Korea suffered a 20% decrease, around 50 tons in rice production. However, South Korea showed little to no negative impact. We then compared the correlation coefficient between drought and yield over a decade. As you can see, there's none. So North Korea had a strong correlation of around -0.7, meaning they had a major impact from drought. However, South Korea had a weak correlation of -0.2, indicating little to no impact. This research highlights the protective effect of stable infrastructures, and we can learn that North Korea has a weaker economy, leading to limited irrigation and are heavily reliant on rainfall, while South Korea is more stable and are resilient against such severe climates. Moving on. We now looked at wider analysis on a larger scale. We examined 4 countries in East Asia, which is located right there. The 4 countries are Indonesia, Laos, Thailand, and Japan. First, we looked at the drought index, which our first speaker explained, but we realized, as you can see, it is pretty random. The numbers are high and low, or like positive and negative, which is like the first row we can see right there. And we realized that like the main problem of this is that 0 being the drought index is actually too much rain for these plants. And now we looked at the optimal drought index, which actually maximizes the crop production. And as you can see here, Laos and Indonesia showed a stronger correlation between drought and crop yield, and Thailand and Japan had weaker correlation, which are likely due to better infrastructures. In other words, India and Laos were extremely affected by droughts, meaning that the production like severely decreased, while Thailand and Japan can actually handle such things and were as affected by such droughts. Okay. And finally, we also considered solar radiation, which is a different factor. And it is very interesting because solar radiation increases during drought because there are less clouds, but actually positively affect crop yields, meaning that if these countries are able to handle droughts, they can actually increase in crop production. And we found similar results as you can see here. And from this research, we found out that such correlations actually fit these countries' economical power and GDP. In other words, their stability and irrigation. Our future plans for this project is as seen here. Well, we believe that we can use this research to make recommendations for future sustainable agriculture. This like rainwater harvesting, efficient irrigation, and soil management, as we've seen from such data. And I believe that with this data, we can boost agriculture and boost economy throughout many countries. And I believe that it can also be practical in solving major global problems right now, as seen as food lack due to overpopulation or climate change. In conclusion of this research, our research shows that economic power is extremely reflected in how well countries handle the impact of climate on agriculture. Wealthier nations such as the US, South Korea, and Japan have stronger infrastructures and are less affected by extreme weather, while developing countries, as I explained about like Indonesia or North Korea, remain vulnerable to droughts and heavy rains. That's it on my presentation. Thank you for listening. We'll be moving on to the conclusion of this presentation.
So thank you for listening. It's like 30 seconds. So throughout all of our presentations, most of us have been focusing on the small scale, daily or even hourly predictions made by GSMap. However, I think it is important to acknowledge that when we focus on the macro, such as the yearly predictions, the GSMap system brings immense benefits to the world of science and beyond. By conducting research such as ours that focuses on the micro, seemingly insignificant weather events, we hope that we can each make our own contributions that combine to improve the system bit by bit and make the place we call home an even better place. And with that, we conclude our presentations for today.
Wow, absolutely astounding, everybody. And for our younger students sitting here for like 2.5 hours, give yourself a huge pat on the back. It is not easy to pay attention for so long. I know you're going to catch a bus, but if anyone has the time to just stand by the astronaut, I'll send just one person up to use my phone because I have everyone's contact information, and I'll share the photo. And then people from Monocacy Valley have a wonderful time as you go and explore some of the museums in town. And thank you so much for making the time and the energy to come. Our other folks, I know we'll be hanging out.